Okay, so I want to address the activity number 2. Um, Basically, the solutions only give the answers, and so let's talk a little bit more about what is actually going on in these solutions here. I think that will be helpful for us. Let's see. Basically, let's just take a look right now at this one here. So we plot some dots, right? So hopefully you figured out how to take this number 2 over here, you go left 2, and then you say let's go with number 15.9, and you say, well, I don't know exactly where that is, but I know there's somewhere you get 14, 15, 16. You say, well, it's probably somewhere around the 16, right? So the point here is not that you get it exact, but that you learn to estimate, and you think about, well, where is that basically, right? Same thing over here with number 5. You go to number 5 here on the time in seconds, and then you go to 10.6 and say, well, okay, here's 10, here's 11, so here's somewhere 10.5-ish, right? So you plotted all these dots, and the idea is you could have just drawn little lines to go, and some of you did, and that's okay, but if you notice that it's actually talking about, they didn't say it exactly in here, but I think did in an earlier place that there was the whole point of this activity has been talking about oscillations. So we were expecting some kind of oscillation, so some oscillatory behavior, and drawing this sort of sinusoidal curve is the kind of oscillation that we're looking for. So anyway, that's the concept there, is that we've plotted some data and we're looking for like a real pattern, and the real pattern is apparent when we try to start to fit some kind of sinusoidal oscillation. So the maximum position that this thing reaches, so we can say that the highest position is maximum, the lowest position is minimum. By the way, these units are crazy. If you think about going up and down, let's say 16 meters down to 8 meters, that's a full range of about 8 meters, which is about 24 feet. So that would be like dropping a giant, this would be like a spring off the side of a building or something. So anyway, they probably could have chosen a little bit better units to make it be something a little bit more realistic or imaginable. But anyway, that's what we have here. And 16 meters is the maximum position. So you can see that here. This is going to be the highest that this thing ever gets. This object that they say, right? The minimum is going to be down to 8, right? So you can see that here. This is the smallest that it gets. When will the object reach its minimum position next? So this question is asking after the last data point that you took. So the next minimum seems to come or somewhere around here at 25 seconds. When will the object reach its next maximum position? Well, it already hit a maximum because this is the last point that we took here was at 22 seconds. But if we keep going, then we can see that there's the next maximum somewhere around here. And if I look, it's maybe around 29, or maybe it's even shifted a little bit over, so it's 29.5. So that's kind of the next when this thing reaches the next maximum position. The amplitude of this motion, as we discussed, is the amplitude is defined as take the center position and go up to the peak. This is called the amplitude of the motion. So from 12 to 16, that's 4, and so you can see it's 4. Also, you can go from the center position down 4, and you should also see that if it's a simple harmonic motion, that both are true. But then just the point to remember is that you might think to yourself like, oh, well, maybe amplitude means like the total, like, maximum to minimum, and it turns out that that's not true. It's the halfway point up to there, so it's actually half that. So it's just something to remember. It's a convention of what amplitude actually means. What's the period of the motion? Period means how long does this thing take until it repeats itself. So that would be this period, it would be this period. It's the time that it takes to go from one place and then return all the way back to the same situation. And so notice I didn't say the same position, because here, if you started right here, you could say, oh, well, it only takes up to here to get back to the same position, but that's not one period, because it's not traveling in the same direction. So it's really when the situation repeats itself. So when you start from here, you go down, up, and then back down, then that's a period. Okay, so let's see, if we went from 2 to, I don't know, looks like 2 up to 11, yeah, 2 up to 11 or something like that, you can see that from 2 to 11 is 9 seconds. if I went from 11 to, I don't know, 20, it actually looks like, I mean, you're guessing here, right? You're estimating. So if I say 11.5 or something like that, maybe this is 2.5 to 11.5. Maybe this is 11.5 to 20.5. So again, 9 seconds. So every 9 seconds, this thing is repeating itself. So we can expect that the period of motion is 9 seconds. Now, the frequency of the motion, that one's not as easy for sure. You could do it a couple of different ways. Visually, you could break up this chart here into even intervals, and you could say, well, how long does it take to, or how much of a cycle does it get through in 1 second? But I think the best way to go about this is to use our regular formula here, which is that the frequency is equal to 1 divided by the period. That's the important point here. And if we take that, I say 1 over 9 seconds, and that gives us 1/9 of a hertz. And remember that hertz is just 1 over seconds, right? So this is like 1 over 9 times 1 over seconds. 1 over seconds is a hertz. Seconds is a hertz. And 1/9, you can plug into a calculator, and you'll get 0.11. So that means it goes through about a tenth of a cycle in a second, which kind of makes sense because it takes almost about 10 seconds, right? It takes 9 seconds to get through a full period. Very good. How many times will this object reach its position in a 10-minute period? Well, in this case, all we have to do is to think about, okay, well, it looks like it's going, 1 cycle, 2 cycles, 3 cycles, and so on. And every time takes 9 seconds. So we could ask the question, if it does 1 cycle, let's do like this. I'm going to make a separate piece of paper here just for our calculation. If it's doing 1 cycle per 9 seconds, then we could ask how many cycles does it do per 10-minute period? Well, here we can say that there's 60 seconds in a minute. And, okay, that's good enough. Now we'll have how many cycles per minute? So we'll have 60 seconds cancels out, so 60 cycles per 9 minutes. That's a good way that we can. So now we have a way to calculate that. Now, I'm going to just use our calculator here. I guess 60 divided by 9 is this number, 6.66666. So, what do we do with that? We round it. We say that this is approximately 6.67 cycles per minute. And so, if I really want to know, we want to say, we want to know in 10 minutes. So, how many, so we know, maybe you can already see the deal is that if it does 6 cycles in 1 minute, then if you want to go to 10 minutes, so how many cycles in 10 minutes? Then we just basically say, I take number of cycles equals to the rate times the time. So notice how I set this up in a way that looks like distance equals rates times time, right? It's actually the same kind of logic here, is that if I want to know, if I'm going 5 miles per hour for 2 hours, then I've gone 10 miles, right? Same idea. So if I'm going 7 cycles per minute in 10 minutes, I literally just multiply them. So going back over to here, the number of cycles that we do, how many times it reaches, it's also encoding for the number of times that the object will reach its maximum position. Also the same thing as asking how many times will the object reach its minimum position. But notice that it's not the same thing as asking how many times it will cross through the center place here. We'll get to that in just a second. So the number of cycles here is going to be 6.67 cycles per minute multiplied by 10 minutes. And you notice that the minutes cancels out, which is multiplying by 10, so we'll shift the decimal place over, so it's 66.7 times, and that is our answer. So we could say 66 or 66.7. Honestly, that's not a big deal here. The big deal is we make sure that we make some sense of things. So they said 66 times, good enough. Maybe they even had been super smart and they realized that actually it would be 66 instead of 67 because maybe it doesn't finish a complete cycle. I don't know. I'm not really worried about it. So the point about that I was just referring to was that they didn't ask how many times does the object cross through this 12, because you notice it would be double, right? So if you saw a question like that and you said, well, how many times does it cross 12 in a 10-minute period? The answer would be double this. It would be 132, I guess, which is twice 66. Cool. All right. Let's practice a few more questions here, and then this will be it for this little mini engagement here around the period and frequency. These are some good problems to practice. I'll work through each one of them individually. So a Foucault pendulum is observed to swing back and forth once every 20 seconds. By the way, for those of you who don't know what a Foucault pendulum is, I encourage you to just look it up briefly, or go visit the California Academy of Sciences. California Academy of Sciences has a really beautiful display of this, and I will offer extra credit for those of you who go and see this pendulum and write something about it. And in fact, I will open up a little section on Blackboard for you to write a little, just a short essay, not essay, but maybe just a couple of paragraphs about your experience to get some extra credit. I'll also offer for you to go and visit some musical events on campus. Those will also be possible with extra credit things. And so I will be posting something, an announcement, and give you a place on Blackboard where you can post about that. But I would like to encourage you really to go and see what this thing is. It's actually really cool. It's some neat physics going on. Essentially, it's a giant pendulum that's hanging from the ceiling of this beautiful building, and it goes back and forth. And so this pendulum is moving back and forth, but what happens is that it goes like this, and I'm just trying to imagine like this. It goes back and forth, and then over time it's actually going like this, and it's precessing in the way that it goes back and forth. And so then they have some little cylinders that are sort of stacked up along the edges, and then once it gets there, it knocks it over. And so it's kind of a fun little thing to guess when is it going to knock over the next one. And the reason why it actually precesses is because our Earth is rotating. And so it's actually it's really cool sort of demonstration that our Earth is rotating. So anyway, the Foucault pendulum, back to our boring problem here, is that this thing goes back and forth once every 20 seconds. What's its frequency? So we can just literally just apply our line formula. Frequency is 1 over period. 1 over 20, 1 over seconds. This is hertz. 1 over 20 is 0.05. If you weren't sure how to do that, you can always plug it into a calculator. That's okay. So 0.05 hertz. What does that mean? It goes through 1/20th of a cycle per second. That's the answer. I want to encourage you to get good at this skill. Okay, next one. While at a running pace, Abigail's heart was beating 170 beats per minute. It's pretty fast beating there. What was the period of her heartbeat? In other words, how long does it take to go through one full heartbeat to the next? And the way we can answer that is that we have to say 170. I'm going to just say cycles instead of beats, but 170 cycles per minute. Let's get this into, we could just take 1 over this, and then our unit would be 1 over minutes, but we already have something called hertz that I think will be helpful for us. So why don't we say 1 minute is the same thing as 60 seconds. Again, that's that multiply by 1 trick where I'm getting rid of the minutes, okay? So I equated 1 minute to 60 seconds, and I said, oh, well then if that's true, then their ratio is just 1. Okay, just to remind you, 1 minute equals to 60 seconds. You can divide both sides by 60 seconds or divide both sides by 1 minute, and you'll have them. Here, this 60 seconds here I'm going to take 170 divided by 60, and I'll have cycles per second. Okay? This is my frequency. Okay? So this was also a frequency here. Let's simplify here. I'm going to take the calculator again. Hopefully you can see this. Reflection. Okay, there we go. And we've got the number 170 divided by 60. 2.83. 2.83 cycles per second. Okay. Now the rest is easy. If I turn my phone on the side, I should be able to do 1 over. So you can see this number here I'm doing is 1 over 0.35. So period is 1 over frequency. That's 1 over 2.83 cycles per second. I'm going to write 1 over second. It's implied that there's cycles or beats happening here. There we go. 1 over seconds. This gives me 0.35 times seconds. There we go. That's my answer. 0.35 seconds, and is confirmed. Okay, good. If you're starting to feel good about these things here, then hopefully the next two won't be so bad. A nervous student taps his foot 7 times every 2 seconds. What is the frequency of his tapping? Okay, so we'll say that the student taps the foot 7 times, so 7 cycles per 2 seconds. And this actually is the frequency, the cycles per second. So we literally just take this here and we say, well, 7 over 2, that's 3.5 cycles per second, or 3.5 hertz. Cycles per second for 1 over seconds is just hertz. That was kind of easy. They already gave us the frequency and they wanted the frequency. So they just wanted us to convert it into a little bit of a different way. So 7 cycles per 2 seconds is the same thing as 14 cycles per 4 seconds, or 3 cycles per 3.5 cycles per 1 second. All those things are true. Okay. If the period of an oscillator doubles, what happens to its frequency? Well, that's kind of interesting. Let's take this. Frequency is 1 over period. If I were to just sneak a 2 in here, well, that's good, but I would have to sneak a 2 down here to make this true. So it looks like the frequency becomes half as much. You could say, I don't really like the language decreases by half, but I think that in this case it works. I would say it becomes half as much. So for example, if the period was 2 seconds and then became 1 second, if it was 2 seconds and became 4 seconds, then the period would go from being 0.5 hertz to 0.25 hertz. So it would decrease by a factor of 2. So we divide by 2. Okay. Well, that's I think all for now. Let me just double check. I think there might have been a couple other points here. Make sure. Yes, there was actually one more point here, which is okay. Oh no. Okay, we got it. I think this is we have all the questions that were. So okay, that is it for the applying new knowledge section of the activity